Good morning. I am Philippe Colonnier from the Japanese French Laboratory for Informatics, a joint lab between CNRS, Sorbonne University, and University of Tokyo. And I will present constraint solving by quantum annealing. So you all know about quantum computing and probably that there are two main paradigms. One, which is a gate-based model favored by IBM, Microsoft, and Google, and the other one being quantum annealing, favored by D-Wave System Incorporated. We want to investigate the use of quantum annealing for constraint satisfaction problems. And for that, we have to model problems in QUBO, which is the input language for the QA system, and to implement on some quantum computer, the D-Wave touch, for instance. So modeling combinatorial optimization and constraint problem in QUBO is easy for simple problems. You have the seminar paper by Andrew Luca, 2014, or the recent tutorial by Fred Glover, 2019. But for more complex problems coming from operational research or constraint programming, it's more difficult. And we'll see, you can see in the paper, quadratic assignment problem, the n-queens, the Costas array, magic square. What is QUBO? Quadratic unconstrained binary optimization. Basically, you have n Boolean variables, x1, xn, and a quadratic expression over x1, xn to minimize. So because in Booleans, the numbers and their square are the same, you can simplify it into this expression, okay, which can be put in matrix format like this. So you have a vector of binarization variable, and x transpose times q times x will be the function to minimize. This is very close to a model which is used in statistical mechanics called the Ising model, where you have spins which can be +1 or -1, which are linked to some neighbors by some couplers. It's a J, the big J are couplers, and they have some bias. And basically the Hamiltonian of this system, which is the energy function, is expressed by this formula H, which is very close to a QUBO. In fact, it's equivalent. You just have to change the variable from being between -1 and +1 to between 0 and 1. Okay, Boolean QUBO. For solving QUBO, therefore, you have two types of solving techniques. The software, you can use CPLEX, or you can use special version of Taboo Search, or hardware, quantum-inspired digital annealing by the Fujitsu, for example, or the real quantum annealing machine like the D-Wave. And you have also others, with the first two, Fujitsu and D-Wave, are commercial systems. The others are just a prototype. The idea of quantum annealing has been proposed in the late 90s by Kadowaki and Nishimori, and it's very close to simulated annealing, except that instead of using the thermal jump to escape from local minima, you use a property called quantum tunneling, which is available in quantum mechanics. So basically, it will make it possible to cross over a thin energy barrier and therefore go from a local minima to maybe a global minima. Later on. I have no time to go into the detail. One point is that QUBO normally is unconstrained. So we want to put CSPs, it's a bit a problem. The idea is to convert, in fact, the constraints into penalties that you will add to the objective function. That's what is done, for example, in constraint-based local search, or also in some framework for soft constraints. So basically, you choose a penalty which will be equal to 0 if the constraint is satisfied, and which will be different from 0 if the constraint is not satisfied. The good point is that such penalties then are compositional. You can add them if you have several constraints with penalty for each of them. You just add them, possibly with some coefficient, if you want a good result. Let's take the first example, the so-called one-hot constraint. So you have a certain number of variables, and you want that among all those variables, only one has value 1. And the others have value 0. So basically, you have a pseudo-Boolean constraint like this. Sum of the xij for all j is equal to 1. Okay. You can have a very simple penalty like that, where you just say that this will be 0 when the constraint will be satisfied. You have to square it because you just want something positive. And if you develop it, you have this quadratic expression. Similarly, for the at most one constraint, you will have this penalty in QUBO that you can also develop, and you have this very simple and nice penalty to add to your objective function. If you want to go a bit to more complex constraints, like the all different constraints, so you have a list x1, xn of variables, sorry, and you want that the value of all of them are different. So if the constraints are into the domain 1n for all, then you will have a permutation basically of 1m, and this is used in many problems as seen here. If you want to use this kind of constraint in Boolean models, you need n2 variable xij, which will be true if xi is value j. And therefore, on those variables, you have 2n constraint to enforce. First line is that, okay, sorry, first line is that each variable has only one value, and the second one is that all values are attained by one variable. Okay, so in Kubo, the same, you will have 2 times n penalties of the following form, which is like the previous one we saw. And if you develop and add all that together, you will have this penalty expression. I don't have time to detail, but you look at the paper, I give some explanation on techniques. So with that, you can model the QAP, quadratic assignment problems. You have the normal objective function, and you add this all different because you want that each facility is assigned to a different location, so all different constraints. It will be described here. Okay, another one, magic square problem. So you have to place all the number between 1 and 2 on an n cross n square, so that the sum of the numbers in all row, columns, and diagonals are equal. So basically, this gives rise to 2n plus 2 constraints for all the rows, columns, and diagonals, and the constraints are on that form. Okay, and you have to add also one all different constraint because you want that all the numbers which are in the square are all different. Okay, so in Kubo, how can you do that? So you will have a Boolean variable, so xijk, which is equal to 1 if xij has value k and 0 otherwise. So you have also the linear constraints that you can express like that. So it's a bit more complicated because here you have a Boolean variable, so you have to make the sum of all the xijk times k. Okay, this gives you the value k, which is currently the one assigned to xij, if you want. Okay, then from that, you have to derive a penalty. Okay, this is a linear constraint, so you can have it like that. Okay, it's a bit more ugly, but that's life. And you have 2 times n constraint like that, so penalties like that, and also one or different constraint like that, as we have seen before. So you add all this up with some penalty coefficient, and you have your magic square problem in Kubo. Last problem, Costas-Array problem. So it was proposed in the 60s by Costas, and there was active community for 50 years. There's still quite a few open problems, so it's very difficult and highly combinatorial problem. So basically what you want on an n cross n grid to put n marks so that there is one mark per line, one mark per column, and also between 2 marks, the difference in line and columns are all different. So if you look at the vector here and here, they are different vectors. All between 2 are different vectors. This is an example of a solution for the 5 times 5 Costas-Array problem. So in Kubo, you can have a similar ID. You will have variable xij, which is equal to 1 if there is a mark on ij and 0 otherwise. And okay, you have one of different constraints, and you have the Costas property, which is expressed like this. You take every quadruplet, not every, but some quadruplet of variable, and if the index are not so good, then you will have to add 1 to the objective function. That's good. Problem, it's not a quadratic function, it's a quartic function, power 4. So you can transform, you need to transform it into a quadratic expression, and this add a lot of new variables. So this is a general problem to convert higher order binary optimization into quadratic and constraint binary optimization. There are several algorithms exist. One of them is the so-called pairwise cover scheme. And if we use it, we have the second formulation of the Costas-Array in Kubo. So basically a variable DAJKL, which corresponds to a couple of marks, one on AG and one on KL. Okay, equal to 1. Therefore, you have much less new variable, n power 4 instead of n power 6. And the penalty to add to the objective function is like that. So between 2 sets of quadruplets, if the indexes are not correct, then you will have to add 1. This one is a quadratic function, so it's okay. Good. There is a question on the front side. Look at the paper for the details, but quickly we will go above what is currently accepted by the quantum annealing or quantum inspired annealing hardware. So that's the first problem. And in fact, it's a bit worse, we'll see later. So just a few words on D-Wave systems. So it's basically a big refrigerator because the CPU has to be cooled down to just a few millikelvin to be operational, but it works. And basically you have qubits, so which are superconducting Josephson junction in a superposition states. And by applying the magnetic field, you will perform the quantum annealing. So basically what you do, you have two Hamiltonians, one which is a simple initial Hamiltonian, and the second which is final Hamiltonian, which is your problem Hamiltonian, which corresponds to the QUBO. And basically you start by the first one, you decrease by the coefficient A, and you increase the coefficient B. And if you do that sufficiently slowly, then you will sure that at the end, the final Hamiltonian corresponds to the minimal energy configuration of your system. I don't have time to go into detail, but anyway, this gives rise to a set of solvers, of QUBO solvers for D-Wave. So first, the real quantum solver, which is called D-Wave sampler, and some hybrid solver, which decompose a bigger problem into smaller one and then do some quantumization on the smaller one. And you're also purely classical solvers, software solvers. There is a problem, I don't have time to go into the detail, but called minor embedding, because you don't have a fully connected graph in the D-Wave. So therefore you need to, again, to add extra variables in order to make it for missing connections, therefore to reduce the size of your problem. So experiments, it's possible for the QFA to encode directly small problems on the QPU directly, but you have infeasible solutions because basically some qubit chains are broken. And for the larger QAP, so you need to use a solver. So here I can show you, but you have more details in the papers. And for constraint satisfaction problems, we can solve also directly on the CPU only n equals 4 for the magic square, and above n equals 10, neither the hybrid solver or QBSolve can find a solution without conflicts. And for cost-star arrays, the same, n equals 8 can be solved, but above n equals 10, then you cannot find a solution without conflict. So conclusion, QUBO is a simple and expressive way to model concentration problems, and it's a good input language for quantum computers, but the current hardware is not good enough to compete with the best heuristic method on these problems, of course, but let's hope that in the next years, quantum hardware will improve, and therefore maybe in 5 years, it will be competitive with the best meta heuristic that we can find now.